Hello there, and this is part 2 of our Chemistry 211 review. Looking forward to finishing this lesson because then we're going to be able to talk about new reactions, new ideas. So that's all coming up real soon. But there's just a few little last topics I wanted to discuss in this review video just to make sure we're all on the same page as we start Chemistry 212. And so the first topic I want to refresh you on is acidity and pKa. Now, acidity and pKa is a very important topic in chemistry, and it continues to be an important topic in organic chemistry. So before we go into what all this is about, I want to refresh your memory in the definition of acid and base. So there's many actual definitions of acids and bases depending on who you ask, but the most helpful definition, I think, is the Bronsted-Lowry definition. So Bronsted-Lowry acid and a Bronsted-Lowry base. So the Bronsted-Lowry acid is defined as a proton donor. So H plus is proton. And an acid donates a proton. And then of course we have the Bronsted-Lowry, and I'm just going to use little ditto marks to show that this is Bronsted-Lowry base. And that's going to be the opposite. It's an H plus, which is a proton, acceptor. Gorgeous. So not everything needs to be an acid or a base. In fact, most chemicals are neither acid nor base. But chemicals that are acids have a proton or hydrogen that they can donate. And substances that are bases have some sort of availability to accept a proton. Let me give you a very typical example of an acid-base reaction. This is not an organic reaction, but something you would have learned at some point in general chemistry. Hydrochloric acid plus water, and I'll draw in the lone pairs, produces. Oftentimes these acid-base reactions are represented with equilibrium arrows, but I don't care about that. If you just want to use a regular arrow, that's fine by me. This is not general chemistry. This is organic chemistry. It really doesn't matter. Now, what would be the product of this reaction? Well, one product could be the chloride ion. And another product could be the hydronium ion. Okay. So this is an example of an acid-base reaction. Take a look. I want you to focus on the hydrochloric acid. Before the reaction started, it had the formula HCl. And now look at it after the reaction is over. Did it gain or lose a proton? That's right, it lost a proton, so that makes it an acid. Because it donated its proton to something else. Water, on the other hand, H2O, look at how it started. It started off as H2O, and it ended as H3O plus. So that means it's gaining a proton, so that makes it a base. We also have names that we give to the products on the product side. So what the acid turns into, so the result of the acid losing a proton, we call that the conjugate base. So that would be the chloride. And the substance that gains the proton, we call that the conjugate acid. So it's a little bit counterintuitive, so you can think of it like the acid turns into the conjugate base, and the base turns into the conjugate acid. Okay, so that's a little refresher on acidity, what the definitions are of acids and bases. And now I'm going to promise to tell you what is pKa. So let's go back to general chemistry yet again. So if you were to write a very generic acid-base reaction, a generic form of this reaction that I just wrote here actually, instead of writing HCl, let's just make it very generic with HA, where A is some anion, could be chlorine, could be iodine, could be sulfate, could be nitrate, could be acetate, some ion A. And we react that with water. And like I mentioned, these are often represented as equilibrium reactions because they don't always go to completion. The products would be A minus plus H3O plus. So what have I done here? I've just rewritten the previous reaction in a totally generic form. And what did that mean? That meant that instead of specifically using hydrochloric acid, I could use any acid that I'm abbreviating with A. We can then define a constant called the KEQ, which is a measure of how much in the forward direction a reaction tends to go. And if you recall from your chemistry classes in the past, KEQ is defined as the concentrations of the products divided by the concentrations of the starting materials. And what we need to represent here, we need to remember that H2O is not included because it's a pure liquid, and we do not include pure liquids and solids in the equilibrium expression formula. And so this fraction here, the concentration of acid times the concentration of conjugate base divided by the concentration of the original acid, we call that the Ka value. And you can kind of have a qualitative understanding of what this Ka value represents. If the reaction proceeds very strongly to the products, that's going to make the numerator very large, and the denominator is going to be very small. So Ka is going to be a very large value. This is true for strong acids. So for very strong acids, they are going to very strongly dissociate into their conjugate base and conjugate acid. That's what strong acids do. They fully dissociate. So those have Ka values on the order of, 10 to the 10, very large numbers. For very weak acids, the concentration of hydronium in the conjugate base is going to be very, very low because they don't tend to react very readily with water. The net result is the denominator is going to be extremely large because the reaction is not going to proceed very far in the forward direction for a weak acid. So the Ka value tends to be very small. Something like 10 to the minus 50, and a very, very small number. Now, these numbers are not very convenient for people to talk about, 10 to the 10, 10 to the minus 50. These are kind of like, extremely unwieldy numbers. So chemists decided, well, let's use something called pKa to make the numbers more convenient. So pKa can allow us to make the numbers more convenient. And so then the pKa scale goes from, the pKa scale looks kind of like a line. And on one end, you've got the pKa. So remember, P means the negative log of Ka. So if you took the negative log of this number, you would get negative 10. And if you took the negative log of this number, you would get 50. So the pKa table roughly spans from negative 10 to positive 50. Very weak acids are here at the top, and very strong acids are here at the bottom. And different organic molecules we can position along this spectrum. And so that is why we have what is called the pKa table, which is right here. So here's the pKa table. You can see that different functional groups have different pKa's, and of course all these values are approximate. Small changes in the structure can have large effects on the pKa, but like for example, carboxylic acid generally has a pKa value of around 5 versus an alcohol, which typically has pKa value of 16, an alkene, pKa value of 43, and so on and so forth. So I do ask you to memorize this pKa value table, which I will post to Canvas to allow you to review if you haven't memorized these values already. It's going to become very, very important in this class to know these numbers. It's going to give you a chemical intuition that's going to be helpful for solving problems. And it's just important to recognize here that the lower the pKa value, the stronger the acid. So for example, our strongest acid on the table would be hydrogen iodide with a pKa of negative 10 is a very strong acid. The weakest acid on our list would be an alkane. At pKa 50, that is an extremely weak acid. What does that mean? It means that the proton that I've indicated in red is not likely to be donated. It's very strongly bonded to whatever it's originally attached to. So that hydrogen that's attached to carbon in the alkane form, it's not going anywhere. It's a very strong bond. It's not likely to be broken. On the other hand, when hydrogen is attached to iodine, that's an extremely weak bond. It very easily and readily wants to break apart. That makes it a very strong acid because that hydrogen is more easily donated. Fantastic. Okay, let's go on now and just talk about a couple more things from Chemistry 211, and then we're going to be done with our review, and then I'm going to release for you a worksheet to make sure that there's no issues or areas where you need more practice. In Chemistry 211, we reviewed countless reactions. And I'm going to be releasing a summary of all of those reactions that we covered. That way you can just keep track and make sure you know all of them, because I do expect you to continue to know all of them. It's possible that you had a different instructor for Chemistry 211, which means that our expectations may not perfectly align. So you need to review the list of reactions that I posted to Canvas and make sure that you are familiar with each and every one of them. Now, I'm not going to be purposefully trying to test you on things from the past, but you just need to be aware of it because it does kind of come up, and we are building on what we learned on Chemistry 211. So you do need to know it, even if it's not the main focus of the course. I did, though, want to kind of review my method for predicting SN2, E2, SN1, and E1 reactions, as that does come up in this class, and I want to make sure that you remember how to do that. So first thing I want to mention that we are going to be sticking with the 5 good leaving groups. And when we talk about good leaving groups, what does that refer to? Well, it refers to the SN2 reaction, the E2 reaction, the SN1 reaction, and the E1 reaction. Now, I expect you to have a general idea of what all of these reactions are. If not, you need to go back and review your Chem 211 class notes. But when I'm talking about the 5 good leaving groups, what I'm referring to is that each one of these reactions is going to require a molecule that is attached to one of these 5 good leaving groups, and they are iodine, bromine, chlorine, water, or sulfonate. Those are the 5 good leaving groups. So whenever you're doing one of these reactions, you need to make sure you have one of those leaving groups present. All right, now, how do we predict between SN2, E2, SN1, and E1? We're going to be using something that I call the table method, which is something that I kind of invented. It's based on many different textbooks, and I kind of just put it all together. So if you haven't taken me before as an instructor, this is going to be something new, which is one of the reasons why I wanted to review it with you. The table looks like this. It has 3 columns: the SN2 column, the E2 column, and the SN1, E1 reactions share a column. Okay. And now for each column, you're going to have to rank a putative reaction as good, fair, or poor. So this will be good, fair, or poor. And there's also a not applicable category for each reaction. Actually, there is no NA for the SN1 column, but for the first 2 columns, there's an NA condition that you need to pay attention to as well. For the SN2 reaction, that reaction is going to be considered good if the molecule containing the leaving group is primary. So if you have what's called a primary substrate, that is good. Secondary is fair for SN2, and tertiary is poor for SN2. The SN2 reaction is considered not applicable if you have a poor or bulky nucleophile. And to refresh your memory from Chem 211, the poor nucleophiles we considered as water, alcohols, and carboxylic acids. and strong acids. Things like hydrochloric acid, hydrobromic acid, strong acids like you learned in general chemistry. Those are poor nucleophiles, so they don't participate in SN2 reactions. For bulky, there's not like a clear definition of what makes something bulky, but just to keep things simple in this class, we're just going to consider bulky as the tert butoxide anion. So it's a tert butyl group attached to oxygen with a negative charge. That's considered a bulky base and won't participate in SN2 reactions because it's too bulky. For the E2 reaction, to determine whether it's good, fair, or poor, you actually look at the pK of the conjugate acid of your nucleophile. So if the pK of the conjugate acid is greater than or equal to 16, we consider that good. Between 0 and 16 is fair, and less than or equal to 0 is poor. I'm going to do some examples so that you remember how to do this. The Na condition for E2 is no beta hydrogen. No sp3 beta hydrogen. You need an sp3 hybridized beta hydrogen. Well, actually, hydrogen cannot be sp3 hybridized. What I mean to say is that there's no sp3 carbon with a beta hydrogen, meaning that a hydrogen has to be attached to an sp3 hybridized carbon at the beta position to the leaving group. SN1E1, that is a beautiful column because it's the opposite of the SN2 column. Specifically, tertiary substrates are good, secondary substrates are fair, and primary substrates are poor. I already mentioned there is no Na condition for the SN1E1 column. There's also a special consideration for allylic and benzylic substrates. Hopefully you remember what that means. Allylic meaning that the leaving group is next to a double bond. Benzylic meaning that the leaving group is next to a benzene ring. So if you have primary or secondary substrates, those can actually be considered good if it's allylic or benzylic, and nucleophile is neutral. That is a way that the SN1E1 column can be good. Similarly, it can be fair with a primary or secondary substrate if allylic or benzylic, if the nucleophile is negative. So I thought we would do some examples, but before we do, I just want to remind you, the E1 reaction, you may be wondering, how is it that SN1 and E1 share a column? How can you tell the difference between SN1 and E1? E1 will use a very specific condition, specifically H2SO4 and heat, or tossic acid, TSOH, and heat. Heat is sometimes indicated with a triangle, which is the Greek letter delta, which means heating. Okay, so let's keep this table in mind and do some examples just to refresh our memory. So let me do an example just down here so that we can have the table on the page while we do it. So suppose we had this example. There's a bromine attached, and we're going to react that with NaOAC. Okay, what's the product? What's the reaction? So here are the steps we're going to take to predict between SN2, E2, SN1, and E1. Step 1, what is the leaving group? We need to make sure that we have one of the 5 good leaving groups that I mentioned before. Otherwise, there's no reaction. So in this case, do we have one of the 5 good leaving groups? Yes. Leaving group equals bromine. Number 2, what is the nucleophile? The nucleophile equals acetate. We are eventually going to have to figure out what the conjugate acid of our nucleophile is, so we might as well do that now. So the conjugate acid of the nucleophile is HOAC, which is acetic acid, which is a carboxylic acid, which has pKa equals 5. All right, now we do the table method. Okay. SN2 is going to be fair because the substrate is secondary. If you look at the leaving group is in a secondary position because there's 2 carbons attached to the leaving group carbon. That makes it secondary, which makes the SN2 column fair. The E2 column, we already said that the pK of the conjugate acid is 5. So that means that we have fair, since 5 lies between 0 and 16. That's the fair condition for E2. SN1E1, it's secondary, so that's fair. We don't have any allylic or benzylic condition here, so there's no upgrade to good. And so we actually have a 3-way tie. Looking at our table, it goes fair, fair, fair. So who wins? Do they all win? No, you choose the first best option. In this case, a 3-way tie, SN2 is going to win because it's the first option. So there is no best option, but there is a first option, and it's the SN2 column. So the winner is SN2. And as we recall, the SN2 reaction is going to be replacement of the leaving group with the nucleophile. So the product of the reaction is as follows. Remember, SN2 proceeds with inversion of stereochemistry, so instead of being wedged, it's going to be dashed. And our nucleophile, OAC, is going to replace the leaving group. Remember that sodium is simply a counterion, and so is not incorporated into the product. And so that's an example of using the table method. Let's do one more using the table method. If you want, I'll write out the problem, then you can try and pause it and do it yourself. And we're also going to do a bunch of these videos, a bunch of these examples during our Zoom live meetings. So here's another example I've got for you. All right, what's the product of this reaction? Try and predict the product. If you want, pause, go through the steps we just went through and see if you can do it yourself. If not, let's do it together. So step 1, do we have a good leaving group? Yes, we've got bromine. What's our nucleophile? Well, remember the sodium's a counterion. It's a spectator ion, so the nucleophile is OET minus. We call that a ethoxide. The conjugate acid equals, well, to make the conjugate acid, you just add a hydrogen. So that would be HOET. What's the pK of HOET? HOET. Well, what is HOET? It's an alcohol. The structure looks like this. It's an OH group attached to an ethyl group. pK of that equals 16. Now we're ready to do our table. Okay, looking at the SN2 column, the substrate is tertiary, so that's poor. The E2 column, the pK of the conjugate acid is 16, which is good. And the SN1E1 column, it's tertiary, so it's good. Okay, so we have poor, good, good. We choose the first best option. The best option is going to be good, but we have to choose the first good, which is E2, going from left to right. So E2 is the winning reaction. How do we draw the product? Well, remember, the E2 reaction makes an alkene. So let's refresh the memory. Let's refresh our memory of the mechanism of the E2 reaction. The E2 reaction is going to remove one of the beta hydrogens to form an alkene. We actually have quite a few beta hydrogens. I can draw them all in. We've got 2 beta hydrogens to the right, 3 beta hydrogens to the left, and 1 beta hydrogen to the top. Which one of those carbons would be considered the priority beta hydrogen? That's right. It's going to be the carbon that bears the fewest number of hydrogens because that's going to lead us to the most substituted alkene, meaning that this is the priority beta hydrogen. Feel free to ask me if you weren't sure what I just said there. I know it was kind of a mouthful, but the priority beta hydrogen is the hydrogen on the carbon with the fewest number of hydrogens. And the reaction mechanism is going to be such that the nucleophile is going to act not like a nucleophile, but as a base. So here's our OET minus. I'll draw the sodium counterion kind of floating around here. The OET minus is going to grab the priority beta hydrogen. That bond is going to collapse to form a double bond between the alpha and beta carbon, and the leaving group is going to be ejected. Stereochemistry is destroyed in the E2 reaction because the hybridization changes from sp3 to sp2, and so the product looks like this. All right, if you got that, excellent. You're in good shape to continue on in this class. If not, I'm here to help you review during week 1. I want to help you get caught up. Obviously, you're not going to be able to relearn all of organic chemistry in 1 week, but my hope is that during this review week, we can focus on the most important things, like this is really important, making alkenes, and just getting you up to speed. So I'm going to create a lot more practice problems, but these are the concepts that I really want you to know for Chemistry 212, and we're going to start learning a bunch of new reactions starting in the next lesson. Okay, bye for now.